Hello friends. So today we are going to discuss few questions, or rather we can say three questions, and these three questions will be from rotational motion. And one second. Okay. So we are going to discuss three questions, and these three questions are from rotational motion. So in the first question, it says that a basketball of radius r rolls without slipping around the inside of a fixed basketball rim of radius capital R. The ball moves such that the point of contact traces out a greater circle of ball's surface, and the center of mass travels in a horizontal circle with the angular velocity of capital omega. At each instant, the radius drawn from the ball's center to the contact point makes an angle of theta with the horizontal. See the figure. Figure we can draw later on. The ball has mass m and moment of inertia I, which is given as 2 by 3 mr square. Assuming pure rolling and steady circular motion, determine the relationship between the angular frequency omega and the geometrical component, that is our r, small r and theta, and the dynamics of balls are to be discussed. Okay. So let me draw the figure, and we are given a ring, or we can say basketball ring, we can also call it as a hoop. So this is the hoop, and within this hoop we have a basketball which is traveling around this rim. Okay. So I'll draw the basketball something like this, okay, so that it becomes more of a clear. And the radius of this rim is given as capital R. So this is the radius capital R, and if this is our center of this ball, that is our, sorry, I think it got lost somewhere. One second. Okay, so we were drawing a hoop, and that hoop was something like this, and we have our, this is small r, okay, and the angle between the two is given as theta. Okay. The point of contact is making angle of theta, so this is our angle of theta. So this is the basic diagram, and we will discuss this basic diagram time and again. And so we are given that we have a basketball and its radius is given to us as a small r, okay, and it rolls around the rim of radius capital R, okay, and we have to remember that there is no slipping, okay, so we can say it is without slipping. So therefore we can draw a certain conclusion from this information that is given to us, and from here we can say, so while it rolls, the first point we can say that the center of mass moves in a horizontal circle. You can say center of mass moves in a horizontal circle, okay. And secondly, that is also given to us in the question itself, which states that the contact point between the ball and rim moves in along a great circle of the ball, along a great circle of ball, which basically means it will be moving, you can say, along the circumference, okay. It is mentioned in the question also, okay. It is given that great circle on the ball surface, so it is given in the question itself. And now we come to the angle part. So it is mentioned that our line from center of mass to the contact point is at an angle theta from horizontal, which we already shown in the picture. And let us assume that our center of mass rotates around the rim with angular frequency, and that is our capital omega. So which basically means that if it is our rim, and for the sake of convenience let us assume this is the ball, okay. So it is moving around the rim with the angular velocity of frequency of our omega, okay, and which we are supposed to find out. So but we have to remember here that, okay, and we have to find out this omega by making an analysis of its motion, that is the motion of this basketball in a rotating frame, reference frame. Okay, so let me put it here, and later on we can discuss its significance because we have to change the frame of the reference. Okay. So therefore you can say that find omega by analyzing the motion in a rotating reference frame. And therefore we are going to start from here only. We start with our that switching to rotating frame. Switching to rotating frame. And in this case we consider that we have a frame that is rotating with the angular speed of omega, and its direction is in the z unit vector. Okay. So we can say that consider a frame rotating with angular velocity, that is omega z unit vector, and in this particular frame the center of mass, the center of the ball, we can assume that is it at rest. Okay, because in the first case we have said that the center of mass is moving in our omega, and now we assume that this frame itself is rotating. Therefore the contact point or the center of ball, we can assume that it will be stationary, okay, or we can say it will be at rest. Therefore we can say in this frame the center of the ball is at rest. Okay, so that's the meaning of switching the rotating frame. And so this non-rotating frame, we can draw certain conclusion from this point. First we can say that in this case we said that the frame is rotating or spinning with the angular velocity of omega. Okay, so therefore we can say the center of mass rotates with same angular velocity in the lab. Second point, we can also say that in the rotating frame the center of mass is fixed. In rotating frame center of mass is fixed. Okay. And we already know that our rim is also fixed, so rim is not moving. Therefore, from here we can draw an important conclusion. It means that only the ball's own spinning motion is left to be discussed. Okay. So we can say that now only the ball's spinning motion is left. Okay. So it means, for the sake of discussion, now this entirely analysis is quite simple because we are only going to discuss the motion of the ball in its own spinning motion. Okay, so that's the basic premise of this discussion. Okay. Now the second thing we are given that, or we can say that okay, therefore we can write that the ball spins with angular speed, and let us suppose the angular speed is given as omega naught. Okay. And we can draw its direction also. So let me redraw the figure, and there we can draw the direction also. So we have this is our radius r, which is of our ring, and we have our ball, and that ball is having a radius of r. And this is the center of the ball. This is the radius r, making angle of theta, and like we said, it is suppose our z-axis, and this will be our we can name this, let us suppose we call this as a x3 unit vector. So this will be the direction of our omega naught. Okay. And therefore we can say the ball spin with angular speed of omega naught about the axis, and this is our minus x3 unit vector. And so let's come back to the rotating condition, which states that there is no slipping, only rotation is there. Okay. And we have already concluded 3 important points, and which are that in rotating frame, the first point is that our center of mass is our fixed. Second point is that our rim is fixed. Okay. And so we can say for the ball, means basketball, to be rolling without slipping, the point of contact momentarily should be at rest. The point of contact must be momentarily at rest. Therefore, we can write that the speed of the surface of the ball at the point of contact, we can just easily derive that. Okay, for that we can say that the center of mass speed in the lab frame and let us call this as VCM will be equal to R times omega, and we can also write the linear speed of the ball's surface due to the spin. You can say the linear speed of the ball's surface due to spin, and let us call this as V surface, and this V surface will be equal to over omega naught multiplied by its radius, that is our R. And these two we can equate them, and this gives us that our omega naught R should be equal to R times omega, or we can say that our omega naught will be equal to R upon small r and multiply by omega. So this is our rolling condition in terms of our rotating frame. This formula we are going to use. Now we come to our angular velocity part. Okay. So now we know that our, let me write it, total angular velocity in the lab's frame. So we can say that the ball has two rotations simultaneously, first one is our rotation of omega in z unit direction, and this is because of the ball's center of mass moves in a circle, and the second one is a rotation which is our minus omega naught x3 unit vector due to its own spin. Therefore, we can say that the total angular velocity and let us call this as omega, and this omega will be equal to our omega z unit vector minus omega naught x3 unit vector. And we already know our omega naught, so we can substitute it here. So we get our omega is equal to omega z unit vector minus r upon small r omega, and this comes as our x3 unit vector. Okay, let us call this as equation number 1. Now we come about the angular momentum about the center of mass. Angular momentum about the center of mass. And the ball is spherical in nature and its moment of inertia is already given to us. So we can see its moment of inertia, which is our I, is equal to our 2 by 3 mr square, that is given to us. And we can write the angular momentum equation formula rather. So we can say that our L is equal to I times omega, and omega we already know, therefore we can write that our L will be equal to I times omega z unit vector minus r upon small r omega and x3 unit vector. Okay. And so from here we can find out the component of this angular momentum. Therefore we can say that the vertical component of this L, it stays fixed. Okay, it's not going to change, but the horizontal part continuously rotates therefore we can write that the component of this, let us call this L perpendicular, will be equal to over I r upon small r, and here we have omega sine of theta. Okay. And in this case we can, because our this the axis which is joining, this is our radius r vector, r rather, not vector, and this is our radius of our ball. The angle between the two is given as theta. And we can suppose this we can divide into two components. This is our x3 unit vector, and we are going to two components, so this is our theta. So obviously this angle will be also theta and this angle will be also theta. So from here we get a horizontal component which is our sine of theta, and the vertical component will be our cos of theta. So So vertical component is not going to change, only this horizontal component is going to change. So that's why we are going to get this as a theta. And now we can, you can say, find out its, so we can say that since the horizontal component of L rotates with angular speed omega, therefore we can write that its time derivative magnitude will be equal to omega times L perpendicular. And we can easily substitute our L perpendicular. So from here we get this as our, we can also put the value of I is our 2/3 mr square, and we have this as r upon small r and omega square sine of theta. And here we can just cancel out this square, therefore we get that dl upon dt will be equal to 2/3 mr multiplied by capital R omega square sine of theta. And its direction will be out of the page. So its direction will be out of the page. And now we can, or rather we can say, we are going to calculate that the torque acting on the ball. Torque on the ball. And so there will be two contributions. One will be because of the gravity, and second one will be from the horizontal centripetal force. So this will be two, you can say, contributor of the torque. Or in the simpler terms, we can also say that the torque comes only due to force at the contact point. So let me redraw the figure again. So this is the radius in which it is going to move, and this is the center, and we have small r its radius, and this is the center of mass. And the center of mass, and suppose this is our vertical axis, and the center of mass is going to rotate in a circle. So this circle will be something like this. And we are given this will be upper angle theta. Therefore, you can say that this part will be our r cos of theta. And the radius of this circle, that is our center of mass, let us call this as our rho. Okay. Rho we can calculate. Rho will be equal to capital R minus r cos of theta. We will calculate it later on. Okay, and along with this, we are going to have a force, we can say mg, that will be acting in downward direction. So first is the torque on the ball. So we can say that our torque comes only from the force at the contact point. Force at the contact point. And we can say there are two contributors and the first one will be torque from gravity, and let us call this as our torque due to gravity as G, and we get this as our mg, and our r cos of theta, okay, and its direction will be out of the page. Direction out of the page. And second, we can say the second contributor will be our torque from the horizontal centripetal force. Torque from the horizontal centripetal force. And first of all, we are going to find out the radius of the center of mass. So radius center of mass we have assumed at rho, and this rho will be equal to r minus r cos of theta. So we can say that center of mass moves in a radius, and that radius is our rho, which equal to r minus small r cos of theta. And we can say the required inward horizontal force and let us call that as our F horizontal will be equal to mass, the radius, and the velocity. And we can substitute the radius, so this comes as m r minus small r cos of theta and our omega square. Okay. And this force will be at a distance of our r sine of theta. Okay. Yeah, so we have this will be our r sine of theta. Therefore, we can write that our torque horizontal will be equal to our minus, and this comes as m r minus small r cos of theta and our perpendicular distance, that is our r sine of theta. So, and its direction we have taken as negative because it will be into the paper. You can say negative because direction into the page. And now we can simply add them. Total torque, so you can see our total torque, that is our tau, will be equal to our mgr and cos of theta minus m r minus cos of theta omega square r sine of theta, and its direction will be outward positive. So therefore we were able to find out the torque. Now almost all the calculation is done, only small part is left, and next we are going to set the torque equal to dl by dt. Okay, that's our, so we can say that set torque is equal to dl by dt, and dl by dt we have already calculated. Okay. So this we are going to equate them, or in the simpler terms we can say that our torque, which we know, is our dl upon dt. So we substitute it, we have our mgr cos of theta minus m r minus r cos of theta omega square r sine of theta is equal to, and dl by dt is 2 by 3 mrr square sine of theta. So this is our 2 by 3 mrr square sine of theta, and we can cancel out the common terms. We can cancel out m throughout, and we can also cancel out our small r. So we get this as g cos of theta minus r minus small r cos of theta omega square sine of theta is equal to 2 by 3 r omega square sine of theta, and we are going to combine the terms of our omega square. So we can write this as g cos of theta will be equal to our omega square sine of theta, we can take as common, and we get this as our 2 by 3 times r plus r minus small r cos of theta. Okay. And so we can further add these two terms. So this will be coming as 5. Okay, therefore we can write that our g cos of theta is equal to omega square sine of theta, and we get this as our 5 by 3r minus r cos of theta. Now it is almost complete now. Therefore we get omega square is equal to g cos of theta divided by sine of theta, and we have 5 by 3r minus r cos of theta. And this is our the required equation in terms of our theta small r as well as capital R. We come to the next question. And it states that a ball is rolling without slipping on a horizontal table. It then rolls onto a sheet of paper. While the ball is on the paper, you can slide the paper around arbitrarily in a horizontal plane. The paper's motion may be smooth or jerky, and the ball may slip relative to the paper during this time. Eventually, the ball rolls off the paper and continues on the table. After a brief transit, it again rolls without slipping on the table surface. Show that the ball's final velocity after pure rolling resumed on the table is equal to the initial velocity before it encountered the paper. So the statement is a lengthy one, but it basically means that when the ball is rolling, before coming onto the paper and after moving out of the paper, there is no change in velocity. This is the basic question. And for that, let us draw. We have a paper, and suppose this is the ball, and we have the center of the ball, and let us suppose the center of the ball is moving at the velocity of VCM, and it's rolling with the velocity of omega. And let us define the, we have our x-axis, y-axis, and z is our out of the paper. So this is our z unit vector, and it is moving. This is the surface on which it is moving, and r is the distance, or we can say the radius of this, the ball. And therefore in the vector form, let us call this as our O and this as a point of contact as P. Therefore we can write that our OP in the vector form, let us call this as our RC, and then this RC will be equal to minus R and our Z unit vector. Okay, this is our O. Okay, it is in the downward direction. And we also know that we are having, or we have assumed that the ball is rolling towards the right. So you can say ball rolling to the right. Therefore we can say that the velocity of the center of mass can be written as V x unit vector. Okay. And from here we can write that our omega will be equal to V upon capital R, and we have this as a Z unit vector plus direction. and we have to simply prove that this initial velocity should be equal to final velocity. So we have to keep this in mind, and for that we are going to make use of the change in the linear momentum and change in the angular momentum. Okay, based on this we can easily prove that our initial and final velocity are not going to change. So let us consider that we have our delta of p, that is total change in linear momentum and we have our delta L, and let us call this as change in angular momentum. Change in angular momentum, and both these changes are about the center of mass. Okay. So it means from the beginning of the pair rolling to the end of the pair rolling. Okay, so it means it starts from the table and ends on the table. In both cases we have a pure rolling motion. So let us start by using the torque and the angular impulse concept. So we can say our torque and angular impulse and there will be the frictional force, let us call this as F of t, that is going to produce a horizontal impulse and torque about the center of mass. Okay, because there will be no other forces. You can say only friction, that is our F of t, produces horizontal impulse and torque about center of mass. So first of all we are going to find out the linear impulse. You can say our linear impulse, and for that we can write the standard formula is our delta of p and integral of our force, where in this case is our friction, and it's d of t. And now we can find out the torque about the center of mass. Center of mass, let us call this as our tau of t, and it will be our r contact, that is a perpendicular distance of the lever arm and multiply by our cross product of our force. And our r of c we have already written, that is our minus r of z unit vector. Therefore we can write that tau is equal to minus r z and f of t. And we can also say, or rather we can know, that our angular impulse is equal to change in angular momentum out center of mass. Our angular impulse is equal to change in angular momentum about center of mass, and mathematically we can write this as our change is equal to our torque and dt. Torque we just calculated. We can write the integral minus r z unit vector and our frictional force, and this is our derivative of t, and we can rewrite this will be equal to our minus r z, and it comes as our f of t and d of t. And we already know that the integral of this force that is here is the frictional force is equal to linear impulse. Therefore, we can say this is minus r z unit vector times delta p. Now let us find out the relationship between our angular momentum and linear momentum under the case of pure rolling condition. So we can say our pure rolling relation between L and P, and for that we can write that our velocity of our center of mass is our r omega, and this is our z unit vector, and moment of inertia, because for a rigid body we know it is equal to k mr square, and k depends upon whether it is a solid sphere or thin sphere. Okay, we can just remodify this value of k, and the magnitude that is of L is nothing but our I times omega. So we can write this as our k m r square, and omega is our v upon capital R, and this r goes by square. Therefore we get this as our k m r p, or we can also write this as our L is equal to k r times p, because m times velocity is our linear momentum, and its direction is obviously parallel to the cross product of our z unit vector and our linear momentum. So we can write this in the vector form is equal to our kr, and we have our z cross p vector, and this will be true for both initially as well as finally. You can see this holds for initial and final, and therefore we have our two expression. Okay, let me rewrite this expression in terms of our this change. Okay, so that is quite simple. We can write this as k of r and z and cross of our change, and we have two equations for this. This is a first equation and this is our second equation. Okay, so we can simply equate them. Therefore we can write that our minus r z cross p is equal to our kr z cross p. and obviously r cannot be equal to 0, so we can simply remove r, and if we combine them we can write this as a 1 plus k, and we have z cross delta p is equal to 0. Obviously 1 plus k cannot be equal to 0 because it is always 1 plus k is greater than 0 for any physical object whose value of k will be about 2 by 5, so it can be negative, and therefore we can write this z cross delta p is equal to 0. Okay. And from here we can furthermore say that our delta p is equal to 0, and this delta p is nothing but our change in linear momentum. Okay. So therefore we can say that our velocity final should be equal to velocity initial. Under this condition only, the change in the linear momentum will be equal to 0. And now we come to the final question, that's the third one. And it states that a solid ball of uniform density rolls without slipping on a horizontal turntable that rotates with a constant angular frequency of omega. As the ball maintains rolling contact with the surface, its center of mass does not remain fixed. Show that, as observed from the initial lab frame, the ball's center of mass moves in a circular path with the angular frequency of 2 omega by 7. So in this case we are given a turntable. So we are having a table something like this, and let us suppose this is our axis, okay, and let us call this our z unit towards the axis, and on this we have placed a ball, and suppose this is the ball, and we have its center of mass. So obviously the ball center of mass is going to trace a circular this way around the same axis, and let us call that our r is its radius, and this ball is having a radius of small a, and its mass is m, and table is rotating with the angular of omega. So in this case we are going to denote use, we can say, cylindrical unit vectors, and these cylindrical unit vectors, let us call them as r, phi and z. We are going to use this. So first of all, let us say that we have a turntable angular speed which is omega, and this is about our plus z, and you can also say that the ball center of mass angular speed about same axis, that is our z axis, about same axis is small omega, and we also say that ball is having a radius of a, and its mass is m, and moment of inertia about its center of mass is given as our I. And we are going to consider, like I said, three cylindrical coordinates, unit vector rather. So we consider the cylindrical unit vectors, and these unit vectors are r, phi and our z. Okay. And here our r unit vector. Okay, first of all let me write their cross product results, which we are going to use later on also, and we are going to denote that of r unit vector cross phi unit vector is going to give us z unit vector, and our z cross r is going to give us phi, and finally we are having our phi cross z is going to give us our r unit vector. Okay, so this we have to remember. Okay. And so in this case, like I said, our r unit vector, this points from the rotation axis towards the ball. You can say points from rotation axis towards the ball, and we have our phi unit vector. It points along the circular path. The center of mass is falling, points along the circular path, center of mass is falling, and z we already know is our, in terms of our axis, that is upward direction. So let us consider a no slip condition. No slip condition because here our this, so for the no slip condition we can say that the contact point, the velocity of the bottom of the ball must be equal to the velocity of the table at the same point. Okay, these two velocities should be equal. Therefore we can say that at contact point the velocity of the ball, and member which is in the lab frame, must be equal the velocity of the table at the same point, at the same point. So this is the basic meaning of no slip condition when our this table is rotating. And now we can simply write the equations of our center of velocity as well as the table point. So you can see that center of mass velocity, and we have to remember this is in the lab frame at radius r, and we can write this formula as our VCM will be equal to omega z unit vector, and this comes as r and our r unit vector. And like we said, here this is z unit vector cross r unit vector, and we have already written that their cross product is equal to a phi unit vector. Therefore, we can write this as our omega r phi unit vector. And furthermore, we can write that the table point at radius r has the velocity, and let us call this as a V table, which will be equal to omega z unit and cross r and r unit. And once again, the r cross z cross r is our phi. So this comes as omega r phi unit vector. So here basically it means that suppose this is our contact point. So this contact point is with respect to the table as well as with respect to the ball, and the velocity of this contact point with respect to the ball should be equal to the velocity of the contact point velocity because of this turntable, because both are moving. Okay, so we have to remember this, that then only it is going to satisfy the condition for our no slip condition. And now we can find out the velocity of the contact point also, because that will be the, so we can say that the velocity of contact point and this also we are talking in a lab frame. Okay. And this will be equal to, let us call this as our V contact, that is our VC, and this VC will be equal to summation of our center of mass plus the rotational contribution from the ball, and rotational contribution of the ball is our omega ball and minus a z unit vector, because ball will be spinning as well as the rotating. And like we said, that our velocity of the contact should be equal to velocity of the table. So these two should be same. You can say that our no slip means that our velocity of the contact should be equal to velocity of the table. Okay, if it's not satisfying this condition, there will be slipping between the ball as well as the table, because the table is also continuously rotating. And we can just simply substitute it now. So we get omega r phi unit vector minus, and second. Yeah, so this is our omega r, and we can just rewrite this as a, because a is the radius of the ball, and this will be equal to over omega ball cross z unit. This will be equal to over omega r and phi unit vector. And we can rearrange, because here I have this phi unit as well as phi unit vector. Therefore, we can write this as our omega minus capital omega, and we have a phi unit vector which will be equal to over a omega ball and our z unit vector. And we can decompose this angular velocity of the ball into the cylindrical coordinates and see which of the coordinates are contributing to this omega ball. So you can say that our omega ball can be written as omega r unit vector plus omega phi unit vector plus omega z unit vector. And now we require the contribution because of this cross product. Okay. Therefore, we can write this as cross product of our z. Okay. And let me put it here, cross product of our z unit vector rather. And this gives us that our r cross z will be our minus of phi unit vector. So this comes as minus of r phi unit vector plus phi, and this phi cross z unit vector will be giving us r unit vector, and this will be z unit z. So this will be over 0. So it means and let me substitute it, and then we can make a comparison of it. So we get this as our omega minus omega r phi unit vector is equal to minus omega r phi unit vector omega phi and our r unit vector. And if you make 1:1 comparison, we can say this our phi, one second, I think I missed something. Yeah, I missed A, sorry. Okay, so this comes as our multiply by A. Therefore, you can say this phi multiplied by A should be equal to 0, or we can say that our omega of phi is equal to 0. So it means there is no phi unit component of our spin. And if we compare these two, and from here we can say that our omega minus capital omega times r is equal to minus a omega r. And we can keep it as it is. Later on, if required, we can just use it. So it means the ball is going to acquire a horizontal spin component, and whose magnitude will be given, and only thing is that the negative sign, it means that the spin tends to oppose the slip between the ball and the table. So that's the only significance of this negative sign. So you can say the sign shows the horizontal spin tends to oppose the slip between ball and table. And now we come to our linear dynamics, that is our centripetal force because of the friction. Linear dynamics, or we can say centripetal force from friction. And we have, this is our ball, and the radius is given as A, and the point of contact, so we are going to have a frictional force F, and this is the center of the ball. And therefore we can write that our frictional force F will be equal to over m and acceleration of our center of mass, and we can write in terms of our omega, so we can say that our F will be equal to minus m omega square r, and we have this as our r unit vector. So F is going to point radially inward, that is only this meaning of our negative. So we can say radially inward. And now we can easily find out the torque about the center. Torque about the center, and let us call this tau, and this tau will be equal to our RC, and we have our frictional force F, and RC is, we already know, this is our downward direction, and A, so this comes as our tau is equal to minus A Z unit vector, and F we just calculated is our minus m omega square r, and we have our r unit vector, and this comes as Z cross r, and Z cross r we know is already our phi, we have defined it at the starting. So we get a torque is equal to am omega square r, and this comes as a phi unit vector. So this is our value for torque, and now we can easily find out rate of change of angular momentum. Rate of change of angular momentum, and we know that the angular momentum, ball's angular momentum rather, about its center, say ball's angular momentum about the center, that is our L, and that will equal to moment of inertia and its velocity of the ball, and this comes as our I, and omega ball we have already calculated. It consists of our omega r and the omega z unit vector, because we know that omega phi is equal to 0. And from here we can write that our dl upon dt will be equal to, this comes as our I omega r, and we have our dr unit vector and of dt. So in this case we know that this is our z unit vector. The vertical vector is fixed, so its derivative, it's not going to change. Only thing that is going to change is our r unit vector, because the ball is rotating about this z unit vector, so its derivative will be equal to 0. Therefore we get this as our I omega r, and this is omega phi unit vector, and we can write this as our I omega r and phi unit vector. Now we can easily say that our total torque is equal to rate of change of angular momentum. So we have rate of change of angular momentum, and we have the total torque also. So therefore we can write that our torque is equal to rate of change of angular momentum. And we can say that our am omega square r is equal to I omega r. And we already know that our A omega r is equal to omega minus omega upon r. So from here we can write that our omega r is divided by A. So on the left side we can substitute it, and this gives us our I omega minus omega divided by A and multiplied by r. And let me write it here, A m omega square times r, and we get this r and r cancels out, and we can cancel this also, square also. Therefore we get this as our A square m omega is equal to I omega minus omega, and we can combine the terms of this omega, and we can write that I omega is equal to our omega I plus A square times m. So it's almost complete now. We can find out our angular velocity. Omega is equal to I upon I omega, and this comes as I plus A square m. And for a solid sphere, uniform solid sphere, the value of I is 2 by 5, ma square. Okay, so we substitute it, we get omega is equal to 2 by 5 ma square times omega, and this comes as 2 by 5 ma square plus ma square, and 5 and 5 cancel out, this comes as 7. So we can say this comes as 2 by 7 ma square, we can take as common, so this will be cancelling out throughout. So this comes at 2 by 7 times omega, and this you can write, which was asked from us, that is omega is equal to 2 by 7 times omega, and here the sign is positive, so which means that it's the same direction, or we can say the center of ball moves in circle same direction as the turntable. So you can say the center of mass of ball moves in a circle same direction as turntable. So this completes all the 3 questions. For today. Thank you.